Hi, everybody. Welcome to this Atmospheric Sciences webinar series. I appreciate you all joining. My name is Rob Rader. I'm the Director of Membership and Engagement here at AGU. We're lucky to have a great speaker today, and I'll introduce her in just a moment. First, I want to let you know that we are recording this webinar today. This is part 5 in an 8-part series for the Atmospheric Science webinars from the past into the future. This was a session held at Fall Meeting 2019 in San Francisco. So the section has invited all these speakers back to talk to you. If you might not have been able to make the session at Fall Meeting or just want a refresher on some of these great topics, that's what Atmospheric Sciences has done for you all today. So we are going to go ahead and get started in just a moment. Kristie A Boering is from the University of California, Berkeley, is joining us today to talk about atmospheric chemistry and climate on a changing Earth. So she will begin her presentation in a moment. I just want to also let you know that you will have the ability to ask your question on the mic during the live Q&A at the end of the presentation. So feel free to stay around and ask your questions. You can also ask them through the application. You'll be able to raise your hand to ask your question or enter your question into the questions part of your dashboard. So with that, I am going to go ahead and hand the ball over to Kristie. And make you the presenter. You are good to go, Kristie. Thanks so much for joining.
All right, we are going to, good morning. I'm going to share my screen here. Did that work?
It looks good. Go ahead and just share your presentation and we'll be good to go.
Yep. There we go. Okay, everyone, good morning, good afternoon, good evening, wherever you are in the world. I hope you and your family, friends, and colleagues are in safe places to hunker down in as we flatten the curve. And I have to say one thing that might be a silver lining. I'm really excited to see the world, the public, talking about curves and how we can change the curves. We're talking about plots, so maybe that's a silver lining here. So welcome. Thank you for joining me today. When Jim and Paul invited me to give this talk on the coupling of atmospheric chemistry and climate, past, present, and future, it was both an honor and incredibly daunting. It is a very big field with many superstars involved over what I'm going to argue is 200 years. But I also want to say this is not really a review. It's a 25-minute tour of some of the highlights that that I have selected. And when I gave this talk in December at AGU, I'd just gotten back from a trip to London. And London is a huge city with massive amounts of history, of course. And so I took about a 2-day sightseeing trip on a bus. And so the analogy that I thought of at the time was, this is like a tour of London in 2 days on a bus. Okay, it's going to be fast, it's going to be superficial, but hopefully it will also be fun. Okay, so I'm going to start here showing you a slide. Here on the left is the view of Earth from Apollo 17 mission, looking at the Earth from far away and seeing it in entirety. In the middle here is a schematic from the IPCC AR5 report showing the linkages between atmospheric composition and chemistry and all of these processes that go in to giving us this global picture of climate. And then here on the right are snapshots of some of the atmospheric chemistry and processes that can influence atmospheric chemistry and climate and vice versa, from smog to the ozone hole, to the wildfires that we're seeing, to changes in monsoon, et cetera. So from looking at this slide, I hope you'll see that there are some challenges here. And some of those challenges are in the very many temporal and spatial scales that are involved, right? From molecular level chemistry to these regional scale processes. And then how do we scale that up to determine their influence on global scale processes? How do we incorporate these processes in models? And then how do we compare these with global measurements? So those are some of the challenges that understanding the coupling between atmospheric chemistry and climate involves. So I like to give this preamble in many talks that I give. I'm not sure who's in the audience. But before I begin, I want to point out what some of the uncertainties are. This is a plot of variations of Earth's surface temperature. It's a deviation from an average in the mid to late 20th century from the year 1000 with predictions out to 2100. So these are estimates of the global mean surface temperature from various proxies, from pollen to ice cores, et cetera. Here's the temperature record here, the known temperature record that goes back to about 1860. And then from here on are model projections. And you can see there are wide uncertainties. But I want to point out that uncertain doesn't mean unknown. The biggest uncertainty in these model projections are what we as humans are doing in the amount of greenhouse gases that we're emitting to the atmosphere. So in that sense, it's uncertain, but we're actually the largest uncertainty, but it's not known. We're not jumping down to much colder temperatures. So I like to point this out because I'm going to be talking about uncertainties. Scientists love uncertainties because we want to resolve uncertainties. We want to know the known unknowns. We want to think up new and exciting unknown unknowns. So scientists are driven by uncertainty and how we can resolve that uncertainty. So we talk a lot about uncertainties. We get excited by them, but so do some of the science deniers get excited about uncertainty. So I want to make sure no one's interpreting uncertainties. There are these uncertainties I'm going to talk about, but they're not unknown. All right. We are, in fact, the biggest uncertainty of all the uncertainties that I'm going to talk about today. So that said, let me get back to the meat of my talk. The tour bus is leaving the station. And the idea that atmospheric composition, what's in the atmosphere, and climate are coupled has a 200-year history. And so in fact, it's 100 years older than AGU. Okay, so I have selected my favorite advances in the understanding of this link between atmospheric composition and climate. I've taken these from a book, The Discovery of Global Warming by Weert. So you can follow up reading on this. It's a nice exposition of this. So it goes back 200 years, just about. We'll soon be celebrating the 200th anniversary of that. It goes back to Fourier. He was the first to calculate that Earth would be much colder without an atmosphere, okay, from the Earth-Sun distance and the interception of that solar insolation, et cetera. Tyndall in 1859 published a paper that demonstrated that, in fact, it was CO2 that's opaque in the infrared and the long wave, and he suggested that role in climate. Right, because until that time, people didn't know that there was anything in the atmosphere that was going to absorb in the infrared. So that is 160 years ago. 120 years ago, Arrhenius published the first calculation of what the warming could be from a doubling of CO2, and that was on the order of magnitude of about 3 degrees Celsius. Kind of similar to what we see now. So it took him many months of calculations with pencil and paper, or maybe, et cetera. I won't go into that. Publishes this first calculation from the doubling of CO2. People didn't really worry about that too much because one idea that was popular was that, that CO2 that now we're starting with the Industrial Revolution to put in the atmosphere was just going to be absorbed by the oceans. So it was Revel publishing a paper in 1957 who made some arguments that, in fact, the ocean is not absorbing all the anthropogenic CO2. That was in line with some radiocarbon measurements that he and Hans Suess were thinking about. Then the International Geophysical Year, right, which we just recently celebrated at one of the recent fall AGU meetings. So the 60th anniversary of the International Geophysical Year in 1957. And that was the time that Dave Keeling started measuring CO2 in the atmosphere incredibly accurately, incredibly precisely, and turns out over long periods of time that showed CO2 increasing in the atmosphere. We'll jump ahead to a mere 40 years ago when Charney led the National Academy of Science reports of the first comprehensive assessment of global climate change due to CO2. And then Jim Hansen in 1981 and colleagues showed that surface aerosols cool the surface. And in 1988 began to talk publicly about it to present the global warming predictions to testimony in front of the US Congress. So this link between atmospheric composition and climate has a long history. All right, how about atmospheric chemistry? What are some historic advances in atmospheric chemistry? For this, I'm following along why reinvent the wheel. I'm using the National Academy of Science, Engineering, and Medicine recent report 2016 on the future of atmospheric chemistry research. And they do a beautiful job of laying this out. In fact, why reinvent the wheel? I'm using a lot of this in my presentation that follows. So this is a great resource for those of you who might want to follow up with additional information. Three major advances that involve thinking about atmospheric chemistry on regional and then continental and global scales. These are also showing the scientists who put forth a lot of these ideas and for whom the US National Medal of Science or the Nobel Prize was awarded. Okay, so these were scientists looking at rapid changes in atmospheric emission and human-induced atmospheric emissions to the atmosphere of various gases and particles, and what the implications would be. So in 1957, Ari Haagenschmidt did experiments as well as just thinking about what all the unknown unknowns might be to understand photochemical smog in Los Angeles, that a mixture of sunlight, nitrogen oxides, and hydrocarbons, these emitted largely by automobile emissions, could produce photochemical smog that is tropospheric ozone as well as particles. And the science that was done really then, an understanding of this then set the stage for policy and to mitigate the air quality effects that it had, particularly in Southern California and Los Angeles, and then out to the globe. Acid rain. Gene Likens was awarded the National Medal of Science in 1972 for carrying out studies at a field site in New Hampshire that emissions of nitrogen oxides, sulfur dioxide, led to the acidification of ecosystems, right? The so-called acid rain problem. I'll point out here another historical fact. Acid rain was actually coined in 1852 by a chemist named Robert Smith, who had studied the acidity of rainwater near urban centers versus out in more clean marine air coming off the coast of England. So it was actually dubbed acid rain, but it wasn't until the 1960s where we were seeing large-scale, continental-scale acidification of ecosystems that led to public awareness and then policies that came from understanding the underlying science that then led to reductions in sulfur emissions from, for example, power plants. And then finally, emissions of CFCs were causing global ozone depletion, or in the future it could, which then came to be with the canary in the coal mine for the cold temperatures that created rapid release of the chlorine that had come from CFCs in the stratosphere that created the Antarctic ozone hole. And both Nobel Prize and National Medal of Science were awarded to Paul Crutzen, Mario Molina, and Sherry Rowland, and the National Medal of Science to Hal Johnston and to Susan Solomon for understanding how human emissions of nitrogen oxides, CFCs, could affect stratospheric ozone, creating the Antarctic ozone hole, and so on. So these are some exciting selected advances in understanding atmospheric chemistry over the decades. I didn't realize until I presented this in December. Now, next, after all these Nobel Prize winners and National Medal of Science winners, I'm now showing you a picture of myself 25 years ago with the graduate student at Harvard at the time, Jen Lipson. We're at a hangar, a very cold hangar in Christchurch, New Zealand in 1994, studying the Antarctic ozone hole by flying instruments to study, out of Christchurch to study the Antarctic ozone hole. So it's a little bit gratuitous, but at the same time, I wanted to fold in my story and an anecdote of at this time, while I was traveling back and forth between NASA Ames or Christchurch, I took taxis on my way to the field work that I was doing there. I sat on people for many hours on airplanes, and when we would talk about what we were doing, I would tell them about studying the stratospheric ozone hole, and people would say, "Oh, yeah, global warming. I've heard about that." And because at the time, to me, there were very different policy implications for that, and it wasn't quite global warming, and it wasn't the stratospheric ozone layer. I was trying to decouple that atmospheric chemistry and transport versus climate, if you will, in people's minds at the time. To me, that was the important thing to do. But of course, now. Um, that is where a lot of the interesting science is, this coupling of atmospheric chemistry and climate on these long time scales. Climate change may in fact delay the recovery of the Antarctic ozone hole. When is it going to disappear? That depends on some of these feedbacks between atmospheric chemistry and climate. So if you want to read more about that in a review form, you can read the WMO's scientific assessment of ozone depletion in 2018, where that's where the active science is now. Okay, so I was trying to separate that in people's minds on airplanes and in taxis when I was doing this work. But in fact, that is where interesting science is today. But in fact, I also have to say that atmospheric chemistry and climate coupling also has a rich history. Yes, it does. So, at the risk of offending people who might be in the audience, I'm going to put all of the history of global chemistry and climate, in my view, condensed into a single slide. Okay, so here we go. Strap yourselves into the tour bus. Here we go for an important tour back to the 1980s. All right, here's the slide that I'd shown at first. This figure I'd shown in the first slide of these processes in which atmospheric chemistry and climate can interact with one another. And so my history here on the right is that Levy in 1971 had solved an interesting mystery. Up until that point, people had largely thought that hydroxyl radicals, the detergent of the atmosphere, hydroxyl radicals were largely confined to the stratosphere. But in fact, that wasn't consistent with the lifetime of carbon monoxide in the global atmosphere, that it needed to be shorter. So therefore, there needed to be a source of OH. CO plus OH is the sink for CO. There needed to be a significant source in the troposphere. Where did that come from? That would have come from ozone photolysis, creating electronically excited oxygen atoms that then react with water. So that was a really significant step forward in some of the interactions between global scale chemical processes with global climate, because that affects methane, for example. And methane is a greenhouse gas. I've got some of these color coded. We got ozone, we've got methane over here. And in fact, this is reviewed in a 1989 paper by Don Webels and Joyce Penner et al. And others, which I will say also, here we go. This is kind of small on my screen and covered up here. This paper references Cicerone, Fahey, Logan, that's covered up on my screen, Michael Prather, Ramanathan, Singh, Ann Thompson, Steve Wassey, probably Michael McElroy, and others. Okay, Sam Altmans. This was truly an exciting time for thinking about global atmospheric chemistry and climate and their coupling in the 1980s. This was also the time, 1987, the claw hypothesis of Charlson et al., that there might be a negative feedback loop in which a warming ocean, okay, emitted more dimethyl sulfide from phytoplankton that created sulfates, which then in turn created cooling aerosols, right? So now we're over here, we've got chemistry, we've got emissions, we've got some biogeochemistry, we've got aerosols, we've got clouds, all happening together. The evidence for this is elusive, let's say. That's how the National Academy worded it as well. There might even be an anti-Cly hypothesis in Lovelock's Revenge of Gaia book published in 2006. But this idea that there's large-scale coupling of chemistry and climate has been researched for a number of years, and these are some of the highlights that I selected for you. All right, the tour continues. You're still on the bus, right? Haven't lost anybody yet. The tour continues. Also, I'm using the format of the National Academy of Science and Engineering and Medicine. This is chapter 3. I'm calling this the known knowns. What do we know? What is our understanding today? That's what chapter 3 is. So here, they've in the report, they've broken that down into 6 things that we know, even though there's still some known unknowns in here as well. So one is that human activities and natural processes both govern emissions that determine the chemical composition of the atmosphere. To do that, we need good inventories of bottom up. How do we estimate what the emissions are? And then how do we check our understanding by doing a top-down analysis from the atmosphere and inverting that using budgets and models, et cetera. I just want to point out some fun recent examples. The ability to measure nitrogen oxides, NO2 specifically from satellites, has really been a boon to understanding how much nitrogen oxides we're really putting into the atmosphere on a global scale, which you can see urban centers. I'll have a plot of that for other reasons later. And people could discover what those emissions were versus uh, some point measurements, extensive still, but not like you could get from a global picture. And we discovered things like the weekend effect, right? That in fact, you can see from space the fact that nitrogen oxides were much lower in urban areas on the weekends when people who weren't driving trucks were largely staying home from work. Oops, excuse me. Why am I going backwards? Okay. Um, uh, so you could use the top down way out from space to understand what the emissions actually were and almost in real time. Wintertime ozone, that was surprising given that it's usually sunlight and as well as nitrogen oxides and VOCs, right? So you're thinking LA in the summertime, or at least I was since I grew up in Southern California during the worst of some of the smog in the 70s. So you think summertime and you don't think wintertime in Utah, but in fact, large amounts of ozone were discovered in the wintertime because we were not understanding to the extent that we do now that oil and gas drilling were causing large amounts of volatile organic compounds to be emitted into the atmosphere. So that was a surprise. Again, when we compare emissions inventories bottom up and check them from the atmosphere top down, we may find that those don't match. And great discoveries are made by doing that. Another discovery, Volkswagen's emission cheating, right? Europeans were starting to notice that, especially where there's a lot of Volkswagens, that bottom up and top down estimates, there was more nitrogen oxides than maybe there should have been. And that was a part of the unraveling of Volkswagen's cheating in having the emissions control on the cars only active when it was on a test bed being tested for the emissions. Okay, so that was something that was discovered by comparing both bottom up and checking them top down drilling. And finally, there's a lot of secondary organic aerosol in the atmosphere, and for decades it's been an issue, right? There's more aerosol than can be accounted for by what we think are the secondary organic aerosol precursors. I'll have something to say about that later. Okay, so this was fun. I went into a lot of detail here. I'm just going to point out other things that we know. Chemical transformations, these fundamental chemical reactions, can affect the spatial and temporal variability of gases and particles. That feeds back into climate. Atmospheric oxidants, very highly reactive compounds like ozone and OH. Those we know control the lifetimes, distributions, and products of emitted species. There's still some known unknowns and maybe some unknown unknowns as well too, but these are established. Chemical processes can interact with atmospheric dynamics, the atmospheric circulation, to in turn control the distribution of trace gases and particles, and vice versa. Particle chemical and physical properties affect cloud and aerosol particle radiative properties, cloud microphysics, and precipitation processes. Atmospheric trace gases and aerosol particles impact and alter global biogeochemical cycles. Okay, so it's a rich field. We know these things to be true, but in here, right, there are things that we understand. There's still those uncertainties that scientists get excited about. There are known unknowns, and there also are some unknown unknowns. So that is the state of understanding. From that, okay, again, I'm calling this some known unknowns. anticipating tomorrow's section of Chapter 4 and 5 of the Academy report. So I want to dig down into this a little bit further, how atmospheric gases and particles affect weather and climate and vice versa. So the effects of well-mixed greenhouse gases, long-lived greenhouse gases like CO2 on a global scale are, I'm putting in, relatively well understood. And that leaves known unknowns in a few of these categories. So I've selected a few of these. I'm going to go into a little bit more detail in two of these, and then I'll be done. Um, the impacts of short-lived species, short-lived is in less than 20 years, or in some cases a lot less than 20 years, such as methane, tropospheric ozone, and black carbon. You know, for one thing, if we can decrease those species that are can influence global climate on a smaller scale, on a shorter time scale, um, then we might be able to save a little bit of have more time to deal with sort of the larger CO2 emissions problem. But there are things that we still need to understand about some of these processes. Very current now, what are the feedbacks between climate and biogeochemical emissions, such as wildfires and storms? What are some of those feedbacks we're seeing that are that are coupled into climate change and biogeochemical changes and ecosystem changes, and what are those feedbacks? There's some interesting unknowns there that we can already anticipate and that people are working on. What's the impact of aerosols on climate, especially their influence on clouds? And that includes natural and anthropogenic sources of the precursors for the aerosols, chemical transformations that can affect the light scattering of the particles as they age. How do they take up water? And hence, what's their ability to act as cloud and ice nuclei? That's a huge field. That's probably 2 AGU review talks in and of themselves. Okay, so I'm not covering that, but I want to bring this into what are some of the exciting known unknowns for the future. And how will atmospheric changes in the stratospheric circulation that are driven by changes in ozone and the well-mixed greenhouse gases that affect radiative forcing and therefore temperature gradients, how do those affect the distribution of stratospheric species, and how will transport of stratospheric ozone into the troposphere, how will that change tropospheric ozone in a changing climate? Okay, so these are some of the exciting known unknowns that a number of our colleagues are working on in atmospheric sciences. In the last few minutes, I want to do 2 short vignettes of some interesting problems. Vignette number 1 is my favorite. Is the stratospheric circulation accelerating due to chemistry and climate changes? And how are we going to figure that out? I'll spend a couple minutes on that. And short vignette number 2, why isn't LA smog improving given continuing decreases in nitrogen oxides and VOC emissions in the area? Okay, so let me do those 2 short vignettes and then I'll conclude. Okay, for vignette number 1, I want to take a new look at old air in the stratosphere. So ever since GCMs had enough computer resolving power to put in a real stratosphere, chemistry climate models have predicted an acceleration of the stratospheric circulation due to changes in radiative forcing and ozone. Basically, it's changing the temperature gradients in the stratosphere, changing the propagation of waves that are driving the stratospheric circulation, changing that, and then the prediction across many different models, in fact, all models, is that the stratospheric circulation is speeding up. So here is a schematic of air that enters the stratosphere from the troposphere with upwelling into the stratosphere. This is the Brewer-Dobson circulation. It goes up, over, and down. There's substantial horizontal mixing here. But the idea is that the circulation is speeding up as the temperature gradients may be changing. I want to say before before I highlight one effort for that, why do we care? Why do we care if the stratospheric circulation is accelerating or not? Well, for one thing, as I noted up here, that is a climate change signal that is robustly predicted by stratospheric resolving models, but it hasn't yet been observed, right? The surface is warming, the stratosphere is cooling, right? Both robust predictions that we have observed, but the fact that the stratospheric circulation is accelerating has not yet been observed. So it's just from a fundamental scientific point of view. But other interesting corollaries of that, the timing of the Antarctic ozone hole recovery and the lifetime of ozone depleting substances will be affected by the strength of the stratospheric circulation, and those may change. Furthermore, there's a dynamic coupling of the stratosphere and the troposphere, and that's known, again, since people have been putting stratosphere in their models, that in turn can affect both weather on shorter time scales and climate. There are other climate feedbacks that could be affected by an acceleration of the stratospheric circulation, increases in upper tropospheric water and ozone, perhaps, particularly where those trace gases have the largest effect on radiative forcing and therefore climate. And then perhaps we'll be bringing more stratospheric ozone down to the surface, and that can affect both policies we're trying to enact and what the levels are of what's caused by humans down here at the surface by emissions versus what's coming down from the stratosphere, and of course the human health effects. So those are the reasons we're interested in that. And yet, we're not seeing that. Here's a 2017 paper by Engel et al. That's taking SF6 and CO2 measurements, taking their time lag with respect to the tropospheric concentrations to infer what the mean age of air is at different locations. And these happen to be for Northern Hemisphere, largely for Northern Hemisphere mid-latitudes, right? So these are the mean ages. If the stratospheric circulation is speeding up everywhere, the mean ages should be decreasing. We're not seeing that trend yet, okay? Now, it may be that we have real tracers. They're not an ideal tracer. And maybe we're undersampling. As a person who likes to go make observations, I'm always going to argue that we've undersampled, but particularly here. Anyway, these characteristics might render a trend, if it's there, in the noise. Okay, that's one idea. You can also measure other tracers besides these inert tracers to get the mean age, ozone and water vapor, temperatures. Other observations over these same time periods are kind of ambiguous, right? Maybe the lower branch of the Bureau-Dobson circulation is speeding up, maybe not. What are the changes in ozone? Ozone's complicated. There are a lot of things going on potentially there. Those turn out to be ambiguous. And so together, these motivate going back to the middle atmosphere to make balloon observations with a test flight that's been funded, armed with some new theory. Okay, so I have a slide or two on this, right? Matador stands for Middle Atmosphere Transport Timescales, Age Distribution, and Ozone Recovery Test Flight. That's an in situ return after arguably about 2 decades back to the middle stratosphere to make some more observations. I'll speed up a little bit here. We are going back to the stratosphere with tracers that we can measure that give us information on the mean ages of stratospheric air, what the width of the age spectrum distribution is, what are residence times, to go back and map our age nitrous oxide, that's a tracer in the stratosphere, uh, uh, that is measured in satellites, right? We want to go back and see if that's changed, and then compare that with 20-year records of satellite records. And the motivation for doing this is we're not just getting a bunch of profiles again. It's motivated by advances in theory by Mariana Linz and Alan Plum that show that if you have the measurements of the mean age gradient, so we're going to go take those new measurements, go back to what we last measured arguably in the 90s and early 2000s, take those tracer measurements of ages, these transport timescales, map that on to N2O as our transfer function, if you will, and get the mean age gradients globally over 20 years from satellite observations, right? And then we can monitor these observation-based fluxes from space. Again, there's measurements from MLS that go from 2004, I think, to the present. I think it's still operating and motivating perhaps some new N2O remote sensing instruments. So here I was advertising, but you can go look it up on the abstract if you'd like. There was a Thursday session at AGU on remote sensing of the middle atmosphere in which Mariana had presented some work. So that is an ongoing effort to take a new look at old air in the stratosphere to try to detect if the stratospheric ozone layer is accelerating. Okay. All right, vignette number 2. I can do this in 2 minutes and then we're done. There's not another speaker, so I think I can take 2 more minutes. I was told I could. I'm going to take the liberty of doing that. My vignette number 2 was the idea that decreasing NOx emissions is happening in LA, but without drops in the smog levels. What's going on with that? Well, changing emissions may bring us into new and unexpected chemical regimes. What about, not only are there known unknowns, maybe there's some unknown unknowns out there. So uh, this vignette was inspired by a talk that Paul Wenberg of Caltech gave at the Hal Johnston seminar the week before I gave this talk at AGU. So this at the time was completely hot off the press from Paul Wenberg's talk, and he gave me permission. I take all the blame if I'm misrepresenting that. So as I'd mentioned earlier, these are trends in NO2 observed, trends from 2005 to 2011. This is a paper out of Ron Cohen's group. They're trends in the OMI satellite NO2 observations over the United States with the effects of emission control technology and the recessions. But you can see there are decreases in nitrogen oxides here. Here's some data that I took off the Air Resources Board website of the ozone trends from 1990 to 2018 and PM 2.5 particles in smog that we care most about for health effects from 1999 to 2018. And you can see since about 2010, LA is kind of skipping around here. So even though NO2 is decreasing, smog is not. What's going on with that? Okay. Well, what came out in Paul's talk and some of the things that he's working on is changing emissions are bringing us into a new unexpected chemical regime. So what happens when the NO concentrations drop, but the concentrations of the volatile organic carbons do not? So I don't expect you to see this because I'm not going to even walk you through this, but we know that if you take a volatile organic compound here, this species, under abundant NOx um, conditions, here's this species forming a peroxy radical that can react with NO. There's several reaction steps with NO. These each produce NO2, and each of those NO2s can go on to produce tropospheric ozone. So these molecules, ultimately through this set of reactions, the molecules fragment and ozone is created. But what happens? These are recent discoveries at low NOx. Okay, so instead, right, so now you take this peroxy radical, it undergoes a 1,5 hydrogen shift, okay, and now you create a single molecule that has, right, a hydroperoxide and an alkyl radical. Then you can add oxygen to that and do some other chemistry. You wind up with bigger molecules and more oxygenated peroxides form, right, that are more oxygenated than the peroxy compound that you started with. So I love this table of contents schematic here, right? You're starting with this peroxy radical and poof, you add all of these extra peroxy radicals from the gas phase autooxidation of these, and you create these HOMs, highly oxygenated organic molecules are formed. Now, the important thing about this is when people look at the chemical composition of the particles, the oxygen to carbon ratio is much higher than expected. And this is a way of forming low volatility, highly oxygenated compounds that will easily condense to form aerosols. So in fact, this may be a key contributor to the atmospheric aerosol and how we were missing some of these secondary organic aerosol precursors. How can we move to see the large amount of secondary organic atmospheric aerosol that we see? And so this is called autooxidation. Even though this was known in condensed phase for years, this was the first time that this was learned to be of importance for the atmosphere itself in gas phase chemistry. And this was also driven by advances both in being able to detect these in the atmosphere, as well as coupling that with some quantum chemical research to understand these processes. So the takeaway is, for this talk, when we're talking about the coupling of atmospheric chemistry and climate, and learning that there are unknown unknowns, and now there's some more known knowns of what may be important. In urban environments, emission control measures are likely to decrease the nitrogen oxide concentrations in the future. So we're going to still keep decreasing this in the future for other good reasons. that may make this auto-oxidation more important. Okay, and with increasing ambient temperatures due to global warming, they become more important as well. So this is a recent discovery that may be even more important in the future. So my concluding slide is, as I take you on this tour, the bus is pulling into the station now. Um, uh, there are many interesting and critical links between atmospheric chemistry and climate. Um, they're the ones that I gave you some highlights of today. What I didn't have time to do was we can learn a lot from thinking about atmospheric chemistry and climate changes in the deep past, for which hindcasting is also going to better inform our future. Some of those questions that people are working on. What were glacial interglacial differences in ozone? What were differences in the oxidizing capacity of the atmosphere? Um, Think about that meteorite impact at the KT boundary. Did atmospheric chemistry and climate coupling, is that actually the main culprit that did dinosaurs in? People are researching that. How do we resolve the faint young sun paradox? That is, why wasn't Earth frozen over when the sun was actually putting out less energy in its first 2 billion years of life, of life, meaning the sun's life? Maybe haze particles that could form from methane photochemistry. People are working on this and other problems. And lastly, I want to make 2 points. Some changes we choose to make on a changing planet, right? As we make technology decisions and changes in our emissions, they have co-benefits. So the Montreal Protocol, an international treaty that reduced ozone depleting substances, those are also potent greenhouse gases. And that has climate benefits. Climate change mitigation and reducing combustion and going to a more efficient energy process can also have air quality and health benefits with less ozone, right? Fewer particles. But I also want to warn there's a lot of unknown unknowns potentially. Some changes may bring no benefits instead of co-benefits. Maybe there's such a thing as no benefits or unintended consequences. Again, warning that there are unknown unknowns that scientists love because there's more puzzles to work out. And that is what I tried to highlight here. If we keep decreasing NOx, which there are good reasons to do that, but with the volatile organic compounds emissions still remaining high, we might get more smog, not less smog. And that is also uh, 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 highlights potential unknowns in geoengineering, right? Stratospheric sulfate injection, seeding marine aerosol. Maybe there's some unknown unknowns in a changing world with this coupling of atmospheric chemistry and climate that we don't know yet. Okay, so thank you. I'm not interrupting the next speaker because there is no next speaker. So I hope you've all been to stay this long, and I'm happy to take any questions.
Thanks so much for that, Kristie. Really appreciate that great talk. And you're right, there's nobody after you, so we've got time for questions, and we've got some questions. So let's go ahead. I'll go backwards just so the questions are relevant to the most recent thing you talked about. What hypothesis, this is from Agnes, what hypothesis do you have in mind regarding glacial, interglacial differences in ozone?
So some of the first papers, I was interested in this when I was looking at the isotopic composition of various long-lived gases, and with my colleagues, Michael Bender of Princeton and Mark Thiemens of UC San Diego and Boaz Luz of the Hebrew Institute. We were interested in what glacial interglacial differences were in ozone at the time, and the only papers that were done 20 years ago were by David Rind and others. Actually, Guy Brazur also had a paper on that. That ozone is a really well buffered system. So in fact, there might not have been dramatic changes in ozone, and that would have implications for life and terrestrial, for various types of life on the surface of the Earth if ozone was changing a lot. The initial work done was that ozone is such a well buffered system that actually you could really change the system a lot, including biochemical feedbacks for N2O and methane, that ozone is so well buffered that actually maybe there were only 10% changes in glacial, interglacial, stratospheric ozone, for example. There are more and more reasons to study that, and even trying to find observations in ice cores that might inform that now. So there may not be large differences because ozone's so well buffered. It took decades of humans pumping CFCs into the atmosphere before we actually saw ozone start tanking in some ways, right? So we're fortunate that it's well buffered, but the initial models have suggested there's not much change, but there's a lot more interest in examining that now.
Thanks, Kristie. Thanks for the question, Agnes. I have a question from Julieta. Your slide mentioned that methane is short-lived, less than 20 years. How does this compare to the lifetime of carbon dioxide?
Yes. So it depends on. Uh, so we know from that methane reacts with OH. That's its primary sink, right? And so that takes I guess the most recent number is about 14 years. If you put in a pulse of methane, it would take about 14 years for that to decay over to 1 over E of its concentrations. CO2 can be hundreds of years, even though there's an overturning of CO2. It has a much longer lifetime in the atmosphere. Some particular pulse that you put in can take on the order of hundreds of years.
All right. Thanks for the question, Julieta. Stanislaus, do you know if there are any studies that try to quantify the amount of methane emitted by anthropogenic sources like rice farms?
Yes, that is quite well studied, and yet there's still some known unknowns about what that might be, especially when methane underwent sort of a hiatus where it sort of leveled off. That was an interesting atmospheric chemistry problem as well, right? Was it emissions? Was it so? And that could have been from rice farming. I'm not an expert in this, but people were studying that there were some changes in how the process for rice production in China in particular was going, and in that I think the fields were not flooded as much, or that allowed oxygen to get in, and the methanogenic bacteria were not pumping out as much methane for that. That was also at a time that the Soviet Union collapsed, and so maybe methane leaking out of the Soviet pipelines had decreased, but certainly people are studying methane from the agriculture of rice production around the world, and that is an active area of study. And there are some mitigation processes that can be done to decrease the amount of methane that's coming from rice production.
That's a great question. Thank you for that. A couple more questions from Jiwoo. First, he wants to thank you for the great presentation. He enjoyed riding your tour bus, as did I. I've heard about that we've got Arctic ozone hole getting bigger recently while Antarctic ozone holes were recovering. I'm curious to know what are the known knowns and unknowns for the Arctic ozone hole.
So yes, so Antarctic ozone recovery, it's still recovering. It's on average getting smaller and slightly less depleted as well, but there are large natural variations as well due to how strong the Antarctic vortex is. For for Arctic ozone, we haven't really even been calling that the Arctic ozone hole because it isn't quite the Antarctic vortex is much less stable, the Arctic vortex than the Antarctic vortex. You can sort of think of that as um, uh, there's a lot more mountains and land, sea, ocean contrasts in the Arctic in the northern hemisphere. So if you think of a bathtub drain, if we want to think of a vortex, you think of bathtub water going down the drain, right? You can have a really stable vortex if you don't have a child in the bathtub with it kicking. Okay, so that's like the Antarctic vortex is like a bathtub with no child in it, but the Arctic vortex that forms, right? That's more like a bathtub with a child kicking, and it breaks up the vortex. So that allows there to be heat and chemical exchanges in the Arctic. But there but some years that have been particularly cold, or that so I guess the child is like cold and getting out of the bathtub earlier, right? Um, uh, the A lot of you may have kids at home, so I'm hoping to uh, tap into the kids in the bathtub idea here. Um, that some years when there's more Arctic, when the Arctic vortex is more stable, then you'll see more ozone loss from that. So that variability is much larger. There's less Arctic ozone depletion in general, but some years it's largely been the dynamics that dictate how much ozone loss there is in the stratosphere. And although again, as things change, there may be some additional known unknowns. You might also be thinking about the so-called Arctic ozone depletion events that are happening in the surface, and that's some really fascinating chemistry. That's not in the stratosphere, but down at the surface. And there's interesting halogen chemistry and feedbacks with the snow, and chlorine and bromine and other interesting things that are happening down low. And those are called Arctic ozone depletion events. And those are really interesting chemistry that's happening. And as the amount of snow and ice decreases, as well as atmospheric composition, there's some interesting potential impacts from that a lot of scientists are also working on.
All right, I think we've got one more question here. This is from Adam. Um, do you have an estimate of the amount of GHG reduction from an extended planetary shutdown like now? And do you know of a source with current monthly anthropogenic contribution data to compare to prior years?
That is very interesting. There are, I know some scientists who are being interviewed by the New York Times and the Washington Post, and there's a lot of interest in that. People who have um, uh, carbon dioxide monitoring stations, and the it's also being measured from satellites. There's OCO2. Ron Cohen and the Beacon Project, BEACON at UC Berkeley, has a number of low-cost sensors and a grid around the Oakland, San Francisco Bay Area. And of course, we were one of the first areas in the U.S. to undergo a shelter at home. So he is monitoring that, and I'm sure a number of other people too. And I think that will be coming out maybe even in the public media soon. It might be too soon. It may be another month before people can determine what it is relative to background, but that information is, I'm sure, going to be coming out soon. And it is an exciting time. Again, we have this unfortunate experiment, just like 9/11 was, to look at the presence or absence of condensation trails from aircraft over the US when only Air Force One was flying. Again, these are unfortunate experiments, but we might as well have science benefit from that. So again, I think from the both from the ground and from space, we're going to be able to see some interesting trends from all our shelter in place.
Thanks, Kristie. So I think that's really all we've got time for. I think we've got some people coming off the call, and we're going to go ahead and end the webinar for today. Just a couple other things to cover first. Kristie, thank you so much. Appreciate your wonderful presentation and for taking the time to share this with our atmospheric sciences members and other members as well. So thank you so much for that. So I'm just going to go ahead and cover just a couple of things here. Let me go ahead and make presenter. So you can find more information about these webinars, including links to the archived versions, which this one shall be up shortly, at the Atmospheric Sciences website webinars page. Here's a quick link to that. I want to thank Jim and Paul for their leadership in bringing these talks to you from fall meeting. I hope everybody found it interesting, and there are a few more left in the series. So definitely reach out to Jim and Paul if you have any interest in getting more involved, or any kind of talks like this that you may be interested in bringing to membership would be great. Next webinar will be next Tuesday on April 7th. Doug Smith and Marika Holland will be presenting to you their talks from 2019 fall meeting. So again, thanks to Jim and Paul and the Atmospheric Sciences leadership. Kristie, thanks again to you. As you all can see, I am remote, as are the rest of AGU, but we are fully operational. And if there's anything we can do for you, please let us know. We're all in this together, and hopefully we'll all be getting through this soon. So thanks so much, everybody, for spending the time with us today, and we'll see you all soon. Take care, Kristie. Thank you.
Thank you.